Good afternoon, everyone. My name is Pearl Hooper. Today, we'll delve into the potential risk associated with the key energy initiatives critical for Saudi Arabia's Vision 2030, particularly focusing on how to mitigate them for a successful implementation. The objective of our report is to assess the risk management framework of the proposed sustainability energy initiatives using risk register, risk matrix, and capital expenditure and operating expenditure. Solar PV is vital for economic diversification, cutting emission, and enhancing energy security. It also creates jobs and lowers fuel costs. Its key brands include ACWA Power, Jinko Solar, and Trina Solar. The LED lighting improves quality of life and safety and enables smart city. The top brands include Shadar, Signify, OSRAM, and Ziumto Bell, offering solutions like Avento streetlights and Shuffle smart poles. Comprehensive risk register systematically identifies potential challenges for each energy initiatives. Each risk has a clear mitigation strategy to reduce its impacts and likelihood, such as using certified long life products or implementing secure protocols. Our analysis shows the initial risk distribution with significant number of risks having high likelihood and impact. However, with the proposed mitigation strategies, we project a substantial shift towards a low and moderate risk profile as shown by the post-mitigation distribution. To put these initiatives in perspective, a medium-sized solar plant with installed capacity of 1 to 20 megawatts has a total capex around 62 million Saudi riyals and an OPEX of approximately 9,40,000 Saudi riyals. For LED lighting, a project involving 50,000 fixtures might incur a total capital expenditure of 10 million Saudi riyals, with an annual operating expenditure of about 5 lakh Saudi riyals for routine maintenance, cleaning, and minor replacements. This chart visually summarizes the distribution of risk across our energy initiatives. Solar plants and PV rooftops, along with thermal insulation, currently shows the highest number of identified risks, indicating where our focus on mitigation will be most critical. These charts provide a quantitative summary of our risk. The first chart shows how the average likelihood and impact have been substantially reduced. The high risk count has dropped to zero and the moderate and low risk counts have increased, signifying a healthier risk profile. The next chart clearly illustrates the before and after average risk scores for each initiative, emphasizing the significant reduction achieved through our tailored mitigation strategies. Our first risk is grid integration. A primary risk here is increased operational cost for grid operators and potential grid instability leading to blackouts. To mitigate this risk, Saudi Arabia needs significant investments in smart grid technologies through implementing advanced grid management systems or forecasting tools, or use of hybrid power plants with thermal storage for backups, or lastly deploying utility scale battery storage, example lithium ion batteries to store excess solar power and release it when needed. The total cost of lithium storage battery for a medium sized plant with solar capacity of 1 megawatts to 20 megawatts designed for storage of 2 to 4 hours of duration can range up to 660 to 1095 Saudi riyals per kilowatt hour. Next, for solar capacity, a risk is losing solar power output annually and underperformance against financial projections due to panel degradation. Our solutions include stringent quality control, sourcing from reputable manufacturers, and regular performance monitoring, and crucially, using sun stimulators for consistent panel testing. A solar stimulator is a specialized laboratory or factory device designed to reproduce the natural sunlight spectrum and intensity for the purpose of testing solar cells and modules. This helps determining a solar panel's electrical performance under standard test conditions. Manufacturers can use them to ensure panels meet specified performance criteria before shipping. Solar simulators can be classified as Class A, B, and C based on their accuracy. Basic Class C and B simulators can range approx 73,000 to 3,67,000 Saudi riyals. However, the high precision Class A simulators can range from 7,35,000 to 3.67 million. Water intrusion poses a significant risk to the inverters, leading to failure, downtime, isolation faults, and component degradation. The mitigation involves selecting higher IP-rated inverters, specifically IP66 for desert storms or IP67 for flood-prone areas, alongside proper mounting and regular inspections. Lastly, a typical IP-rated inverter for a medium-sized plant costs approximately 2,000 Saudi riyals each. Dust accumulation in our desert environment causes efficiency reduction and proportional loss in energy production and revenue. Our solution is twofold: implementing auto-robotic cleaning systems and applying anti-soil coatings. For a medium-sized plant, anti-soil coatings could cost between 1,69,000 to 4,22,000 Saudi riyals. Cracks on solar panel reduces power output efficiency and can void warranties. The solution includes using enhanced glass, ensuring International Electrotechnical Commission certification, and utilizing electroluminescent solar module tester for inspection, with a tester costing approximately $6,000. The EL Solar Module Tester is a crucial diagnostic tool used to identify hidden defects in solar panels that are not visible to the naked eye or through standard visual inspections. It's particularly effective at detecting tiny cracks in the silicon cells, which significantly reduces efficiency and leads to hotspots. It clearly shows broken cells and also reveals any poor electrical connection. Lastly, it also helps in identifying problems like dark cells, which are non-functional areas, and various manufacturing defects. The tester works by applying an electric current to the solar panel. When electric current flows through the healthy PV cells, they emit light in the infrared spectrum. This IR emitted light is then captured by the high-resolution specialized camera. The captured EL image acts like an X-ray of the solar panel. High temperatures lead to degradation of solar panels and inverters, resulting in revenue losses and daily power losses due to overheating. Mitigation involves selecting high temperature resilient panels, optimizing mounting and ventilation, and deploying advanced cooling systems for inverters, complemented by the use of sun stimulators. Cybersecurity are a critical risk, potentially causing operational downtime, significant financial losses, reputational damage, and grid stability risk. Our defense includes implementing robust cybersecurity architecture, conducting regular audits and penetration testing, and investing in continuous employee training and awareness. Specific to LED lighting, a major risk is operational failure and reduced energy savings due to lumen depreciation or sensor failure caused by harsh environment condition and dust. This leads to degradation, loss of brightness, and reduced output. Mitigation includes deploying automated cleaning systems and specifying certified long-life, robust X-proof LED lights designed for extreme conditions. These LED lights are built with high-strength, corrosion-resistant material to withstand the harsh conditions. LED technology provides bright illumination with low energy consumption, reducing operational cost. It is designed to minimize the heat emission, reducing risk of overheating. Lastly, it's built for longevity, reducing maintenance frequency and cost. City lighting also carries the risk of light pollution impacting human health and ecosystems. Our solution is intelligent lighting design and fixture selection, emphasizing shielded and directed light like the Shadar Evento street lighting solution to ensure light goes only where it is needed.
Hello everyone, my name is Abdul Malik. This report will represent the results of a quantitative and qualitative assessment of four major sustainability initiatives. The study includes the risk management framework and also concludes with targeted recommendation for the prioritizing solar deployment. Under Saudi Arabia Vision 2030 and the BIF Net Zero Carbon by 2050, this report will evaluate four sustainability initiatives designed to help achieve these goals. And here's the list of initiatives: solar plants and PV rooftops, district cooling, thermal wall insulation, shading and glazing. Each initiative was assessed for CO2 emission abatement potential, CAPEX, OPEX, MAC, risk profile, loading opportunity, and mitigation strategies. Now moving for approach and findings. Each initiative's abatement potential was calculated based on annual reduction. As we can see, the solar plants and PV rooftops has the highest total carbon reduction for these initiatives, 130 million. And here we can see how we reached to that reduction figures, the assumptions for the each initiative here. The solar capacity, 3 to 5 gigawatt deployed, utility plus rooftop. The average output in the yearly 5,000 to 7,000 gigawatt per hour yearly. The grid emission factor, this is as per Saudi average fossil based. For district cooling, also it saves 30-40% versus the individual chillers. Cooling load saved 15 to 20 million. Grid factor 0.5, 0.6 total CO2 megawatt per hour. Also for the thermal wall insulation, we have the energy saving 20 to 25 applied for 2 million meter square. Grid factor 0.5, 0.6, same as the shading and glazing, saving 10 to 15 kilowatt per hour, applied for 2 million, and the grid 0.5, 0.6, 2.6. And here we have the initiatives CAPEX and OPEX. Firstly, the solar plants and PV rooftops. We have here's the on the left side the CAPEX list. Next to it, the OPEX list also. For the next one, the district cooling. Also, we have the CAPEX and OPEX. Thermal wall insulation. Shading and glazing, CAPEX and OPEX. Now the MBV calculation, cost versus benefits for each initiative here. As we can see that the most benefit will be with the solar plants and RV rooftops. And from the benefit side, for the solar plants, CO2 abatement 5 million per year, multiplying by the 26 years each year. The district cooling 2 million per year abatement. The thermal also we have 1 million total carbon CO2 emission per year, and the net present value it will be 1.17 billion, and the same for shading and glazing. Here is the comparison for the initiatives. As we can see, shading and glazing offers the most cost-efficient abatement. Solar PV provides the highest overall abatement potential. Now moving to the risk management framework, we'll go through the risk register, risk matrix, and risk opportunities. Here is the risk matrix for each initiative and what's the potential risk, likelihood, impact, risk rate, and the mitigation strategy and post-mitigation likelihood and impact. Here is the first two initiatives, and here is the last initiatives. And here is the risk matrix from 1 to 5 likelihood, and the impact also, the severity 1 to 5. As we can see here, the risk matrix before mitigation, mostly it was very high and high. And here, post mitigation, we have only the high one, which is not related to the initiative itself. It's related to the PIF backing, the financing. And here is the risk opportunities. We have each initiative have some opportunities for solar plants, advance in solar technology, falling PV module prices, district cooling technology improvement, government incentives for energy efficiency. For the next one, update to building codes, local manufacturing of materials, and the last one, adoption of smart shading, falling costs of high performance glazing. Here's the conclusion for our report for the four initiatives. Priority initiatives, shading and glazing and solar PV due to a cost efficiency and large abatement potential. This offers the highest total abatement potential and competitive marginal cost, making them a cornerstone of decarbonization efforts. District cooling also provides a significant operational efficiency, though at a higher marginal cost per total CO2 saved. Passive design measures the thermal insulation and shading glazing contribute meaningful to energy efficiency at relatively low marginal cost, particularly when combined with supportive building policies. Thank you, everyone.
Today, I'll present our key findings on material sustainability initiatives in Saudi Arabia. As part of our risk management analysis, I focused on three critical materials initiatives that align with Vision 2030 and offer significant environmental benefits. Let me start with our three core initiatives. First, recycled steel using electric arc furnace technologies with scrap metal versus 4 to 48% reduction cost versus steel and 70% COD or emission percent condi emissions reduction. The Saudi scrap export ban ensures reliable local supply. Second, recycled concrete involves reusing demolition waste as aggregate. Has IRC invest has in 160 million SAR in this sector. achieving 5 to 10% COE reduction with optimal performance using 25% recycled concrete aggregate. Third, local sourcing targets the 160 plus billion-dollar Saudi building materials market and reducing transport emissions by zero point zero 0.05 to zero point 0.1 tons COE per ton. While it has strong Vision 2030 government support, we face supply capacity constraints that need addressing. Our risk analysis identifies key challenges across all initiatives. For recycled steel, market price volatility is mitigated through long-term supplier contracts and hedging mechanisms. Quality inconsistency risks are managed through enhanced quality control systems and supplier certification programs. Local sourcing faces supplier capacity limitations, which we address through development programs and capacity building initiatives. Recycled concrete processing costs as are managed through economies of scale and technology advancement. The financial structure shows recycled steel requiring 50 million CRTPX with 50 million annual OPEX, delivering strong returns. Local sourcing needs 75 million TPX for supplier development with 20 million OPEX. Recycled concrete requires 35 million TAPX for processing equipment with 18 million annual operating costs. Total portfolio investment is 160 million CAR, generating substantial positive NPV. Our comprehensive risk register contains 18 detailed risks across all initiatives using a 1 to 5 scale for likelihood and impact assessment. The risk makes visualization shows most risks are medium level and manageable through our mitigation strategies. High priority risks include market price volatility for steel, supplier capacity for local sourcing, and processing costs for concrete. Our color-coded system helps prioritize mitigation efforts effectively. Beyond risk mitigation, we've identified significant opportunities. For recycled steel, the 44 to 80% cost savings creates competitive advantage in construction bidding and improves project profitability. The 1.6 tons COV reduction per ton creates potential for carbon credit revenue as the Saudi carbon market develops. And local sourcing supports Vision 2030 economic diversification goals by developing domestic manufacturing capabilities, creating jobs for Saudi nationals, and building supply chain resilience by reducing import dependency. Recycled concrete addresses 16 million tons annually of construction and demolition waste, creating new revenue streams. The NovaScrete consortium positions Saudi Arabia as a leader in sustainable concrete technology development. Our key findings show Korea Steel offers high savings, 70% CO reduction, and high implementation readiness, making it our priority initiative. Recycled concrete currently has a cost premium but provides significant waste management benefits with strong long-term potential. Local sourcing has strong Vision 2030 alignment but faces supply capacity constraints requiring strategic development. The overall risk profile is medium risk with high potential returns. Importantly, all initiatives meet green finance compliance under the green buildings category. achieving 45% COE reduction, supporting Saudi 2030 targets, and aligning with UN Sustainable Development Goals 9, 11, 12.
Hello, I'm Roda Al-Shaybani, and today I will walk you through 5 water efficiency initiatives for BH benchmark against Vision 2030 and the PIF Green Finance Framework. Our objective was to evaluate 5 initiatives: alternate water use, efficient appliances, fixtures and fittings, low flush toilets, and shut-off valves using MPV and a marginal abatement cost of carbon. We built a math model, calculated MPV at a 5% rate, quantified water and CO2 savings, scored risk, and checked PIF compliance. And here we can see the 5 initiatives. Under Vision 2030, Saudi Arabia aims to cut potable water use by 20%. Yet our municipal buildings remain well above efficiency benchmarks. Today we are fully dependent on costly carbon-intensive desalinated water, and upcoming tariff reforms, ESG demands, and growing scarcity risk only increase the pressure. To address this, our study evaluates 5 targeted initiatives and recommends starting with condensate recovery and high efficiency fixtures. We have underpinned these choices with detailed MAC and MPV analysis and a 5 by 5 risk mitigation framework, ensuring we not only drive at least 15% green capex savings but also meet PIF's ESG reporting standards. In this slide, we outline the 5 PIF green finance criteria that underpin our entire program. First, green capex. We channel 100% of capital into water efficiency and reuse solutions, ensuring every real qualifies as a green investment. Second, we achieve potable water savings of at least 15% by cutting freshwater demand through measures like condensate recovery and low flow fixtures. Third, our ESG reporting commitment includes quarterly measurement and verification reports that track both water savings and CO2 equivalent reductions. Fourth, we apply a structured risk management process, scoring each initiative in a 5 by 5 matrix and defining targeted mitigations plan. Finally, we perform a full environmental assessment with baseline and post-installation monitoring of water quality and usage to confirm performance and compliance. We start by metering condensate from HVAC drains to establish a baseline yield, then size a route, a collection system, tank, piping, filter, UV using CAD and hydraulic models. Our cost model calculates MPV and marginal abatement cost for both CAPEX and O&M. We verify CASO Class A reuse with a 1 ppm chlorine dose, then pilot 1A HU to confirm water quality and user acceptance. All risk Legionella blockages, pump failures are scored and mitigated in a 5 by 5 matrix. Finally, we demonstrate full PIF alignment with 100% green capex and at least 15% potable water savings, backed by quarterly ESG reporting. We audited kitchen spray guns for flow, then selected 4 to 6 L per minute SASO, 5 ticks or Energy Star valves with local support. Our model calculates incremental capex, opex, and derives MPV and MAC. We convert water and energy savings per cycle into CO2 equivalents. A 10% pilot swap gathers shift feedback on performance. Risks like clogging and delays are scored in a 5 by 5 matrix with mitigation plans. All costs qualify as green capex, delivering greater than equal to 15% potable water savings and meeting our ESG reporting commitments. For this third initiative, we start with a flow rate audit of existing faucets and showers, benchmarking against SASO efficiency limits. We then select fixtures rate at lower than equal to 5.7 L per minute for taps and lower than equal to 7 L per minute for showers. Balancing water savings and user comfort, our cost model calculates both MPV and MAC based on annualized capex and opex. We convert reduced hot water use to CO2 equivalents using the grid factor. A pilot install sample fixtures to gather user feedback on comfort and performance. All identify procurement, installation, and vandalism risk are scored in a 5 by 5 matrix with mitigation plans. Finally, we ensure PIF alignment by confirming green capex, achieving at least 15% potable water savings, and integrating quarterly ESG reporting. For the low flush toilet initiative, we begin with a stock survey to record existing flush volumes, ages, and daily cycle count. We then specify dual flush units, 3 quarters, 4.5 or pressure assist models that meet PIF's 15% potable water savings. Our cost model treats capex as one of retrofit expense and assume zero incremental OPEX under the existing FM contract, calculating both MPV and MAC accordingly. We estimate annual water savings in cubic meters and translate that into CO2 equivalent reductions using the desalination factor. A 10% pilot retrofit monitors clogging, odor, and user satisfaction. All risks such as plumbing failures, misuse, and supplier delays are scored and mitigated in 5 by 5 matrix. Finally, we verify PIF compliance with the green capex, documented water savings, and quarterly ESG reporting. For the final initiative, we will deploy IoT-enabled shut-off valves to actively control leak points. We start with network mapping to locate critical branch pipes, then install valves with ultrasonic flow sensors. A pre-installation leak baseline measures cubic meter per day losses. Our cost model analyzes the incremental capex and assumes zero additional OPEX under the existing FM contract, calculating both MPV and marginal equipment cost. We simulate valve reliability, including false closures and downtime to estimate business continuity risk. A 30-day pilot over 10% for the network will track false alarms and use and user bypass behavior. All cyber security, supply chain, and bypass risks are scored in a 5 by 5 matrix and mitigated. Finally, we verify PIF compliance with 100% green capex, over 15% potable water savings, and quarterly ESG reporting. Condensate recovery cost 110k Saudi Riyal upfront and 15k Saudi Riyal per year, yielding 9,000 cubic meter water savings, approximately equals 67k Saudi Riyal per year and 95 TCOE. It delivers a positive NPV of 544k Saudi Riyal with a marginal abatement cost of 5 Saudi Riyal cubic meter, fully compliant with our PIF green finance criteria. Here our high efficiency pre-run spray valves require just 4.5k Saudi Riyals in upfront investment and 200 Saudi Riyals per year in maintenance, delivering 2,800 cubic meter of water savings, approximately equals 3.2 k Saudi Riyals annually, and avoiding nearly 30 TCO2 per year. The measure shows a net present cost of 32.6k Saudi Riyals and positive NPV of 32.6k Saudi Riyals at 5% with a negative marginal effective cost of 0.94 per cubic meter, making it both economical and highly effective. For our efficient fixtures and fittings upgrade, we invested 6k Saudi Riyals upfront and 500 Saudi Riyals annually for maintenance, yielding 5,000 cubic meter of water savings per year, approximately equals 3.75k Saudi Riyals in avoided water cost and cutting roughly 53 TCO2. The project delivers an NPV of 34.5k Saudi Riyals at a 5% discount rate and a marginal abatement cost of 0.55 per cubic meter, making it a highly cost-effective measure. For the low flush toilet retrofit, we have replaced 30 fixtures at a total capex of 90k Saudi Riyals with zero incremental OPEX under the existing FM contract. This delivers annual water savings of 1.2 case cubic meter, equivalent to 0.9k Saudi Riyals avoided cost and cuts CO2 emissions by 12.70 per year. The net present cost is 78.8k Saudi Riyals with an equivalent annual cost of 6.3k Saudi Riyals. The marginal abatement cost is 5.3 Saudi Riyals per cubic meter saved or 497 Saudi Riyals per TCO2. While the pure financial return is negative, this measure is retained to meet PIF's potable water reduction target and secure 12.7 T of CO2 abatement as part of our ESG commitments. For the shut-off valve initiative, we are installing 10 automated valves at a capex of 8k Saudi Riyals with no incremental OPEX since maintenance is covered under our existing FM contract. These valves are expected to save about 3k cubic meter of water annually, equivalent to 1.5k Saudi Riyals in avoided cost and prevent roughly 32 T of CO2 per year. The analysis shows a negative net present cost of 10.7k Saudi riyals, meaning a net saving, and an equivalent annual benefit of 858 Saudi riyals per year. The marginal abatement cost is highly favorable at 0.29 Saudi riyals per cubic meter saved, reflecting both financial and environmental upside. In the appendix, we have distilled the core takeaways and underlying assumptions. Our benchmarking covered five water efficiency measures using a 5% real discount rate, and MAC and PV analysis aligned to PIF and Vision 2030 targets. Key results show efficient fixtures and low flush toilets offer the lowest cost per cubic meter and fastest payback, while Energy Star appliances deliver combined water and hot water energy savings. Condensate recovery achieves the largest CO2 reduction but a higher cost, retained primarily for ESG compliance. Automated shut-off valves add flood risk protection with near zero incremental OpEx. Assumptions include a 5% real discount rate, asset lives of 10 to 15 years, grade carbon and desalination energy factors, zero incremental OpEx for toilets and valves under existing existing FM contracts, and exclusion of rebates of carbon credit revenues. In closing, a few caveats to note. Our economics are sensitive to future tariff and policy shifts, which could reorder the ranking of these measures. The vendor prices we have used are indicative; actual procurement cost may vary. Performance estimates are based on pilot trials covering up to 10% of fixtures, so full-scale results could swing by around 10%. We have also excluded variables like user behavior, IoT, or could reliability issues, and specific financing structures. Finally, we have assumed a constant grid carbon factor. Any further decarbonization of the grid would enhance the recognized CO2 savings of these initiatives. This register shows the top 6 risks for each initiative, our mitigation steps, and the resulting lower scores. It demonstrates how targeted controls have reduced both likelihood and impact across the board. Here is our risk matrix before mitigation, showing most items clustered in the medium risk zone. And here we can see the risk matrix after mitigation, where every risk has been driven down to low likelihood and low impact. This chart shows how our risk scores dropped from around 6 to 8 before mitigation to under 3 after, demonstrating that our controls have moved every initiative from medium high into low risk territory.
Good day, everyone. In this part, I will present the risk management framework for waste sustainability initiatives. This work focuses on the four key types of waste in alignment with the Saudi Vision 2030 and the Net Zero Carbon 2050 pathway. Waste management areas are critical to environmental sustainability, driven by raising landfill overflow, emissions, ESG investor pressure, and regulatory policies like 2020 Saudi Waste Management Law. The objectives of this paper include evaluating each waste initiative's environmental and financial performance, estimating CO2 reduction, conducting MPV and marginal abatement cost analysis, and identifying associated risks. The economic growth has caused a spike in waste generation. Mismanagement not only threatens the environment, but also poses the serious health, financial, and operational risks. This justifies the urgency for sustainable waste solution. Here we introduce the four key initiatives: managing demolition and construction waste, improving municipal solid waste handling through green practice, and reducing plastic and paper waste. Each initiative has unique operational and environmental challenge which we will explore. Demolition waste includes hazards such as toxic material or sharp debris. Operational safety protocols are critical. Risk mitigation strategies involving a proper segregation, PPE, and compliant disposal method to avoid harm to workers and the environment. In the table here, this is risk identification related to demolition waste, such as unsegregated hazard material, injury from unsafe demolition, non-compliance penalties. Construction waste, often exceeding the projections, leading to cost overrun and environmental strain. Additionally, contractor non-compliance with the waste protocols is a major risk. Solutions include supervision, contracts with the clear waste clauses, and auditing system. Here in the table there is risk identification related to the construction waste, such as overgeneration waste, contractor non-compliance, low recycling rates. Municipal solid waste. Organic waste in the municipal garbage can produce harmful gases if not handled properly. When waste is not sorted, the risk became higher. By using a smart sorting system and raising public awareness, we can significantly reduce this issue and this problem. And in this table, we can see the risk identification related of MSW, like contamination, safety hazard, and illegal dumping. Plastic paper waste. In this segment, we explore issues like fraudulent eco-labeling, which is misleads customer, and poor reverse logistics. Strengthening of regulation and build efficient return system are essential to manage this waste stream. In the table, there is risk identification, the main risk related of the plastic paper waste, such as fraudulent eco-labeling, inefficient reverse logistics, regulatory breaches. This section shows financial costs and analysis for each initiative, along with the time duration, such as CAPEX and OPEX, net present value, cost-benefit analysis, and marginal abatement costs. These tools help to prioritizing the projects based on their financial viability and environmental impact. We'll start by CAPEX and OPEX as per the table which we show four initiatives and estimated amount in CAPEX and OPEX to be invested within 5 years, such as demolition CAPEX required 2.5 million plus OPEX 1 million yearly, so the total to be 7.5 million. Construction 9 million, MWBS 11.7, plastic and paper 8.3 million approximately. Here in this table, we can find the saving per ton if we applying the proper plan of investment in the initiative. We can save, for example, in demolition 150 real per ton, construction 138 per ton, MSW 146 real per ton, and in the paper and plastic 184 real per ton. Cost benefit analysis. We expect that if we applying the initiative in a proper way in our projects to save 50,000 tons in demolition waste, 65,000 tons of construction, 80,000 tons of MSW, plastic and paper 45,000 tons. By Saudi Riyal, demolition will be 6 million, construction 7.5, MSW 9 million, plastic and paper 5.5 million Saudi Riyal. Here is the net present value of financial benefits if we apply the initiatives over the pathways for year 2030, 2040, and 2050. In each initiative, we can see expected benefit by net present value. For instance, in demolition, around 1 million we can save in 2030, 2.1 in 2040, and 4.8 in 2050. The same things it will be applied on the construction, MSW, plastic and paper as shown in this table. Here is the time frame suggestion for the projects. Allocated between 4 phases as we see in the table, starting by feasibility study, pilot testing. Second phase it will be full implementation. Third phase will be technology upgrades, AI adapting and developing. Last stage it will be final optimization and full net zero alignment. This chart shows the impact of waste initiatives before and after implementation in different aspects: CO2 emissions, landfill usage, processing efficiency, professional costs, recycling rate, job created as well. And we can notice that the significant impact which we get and the benefits which we get if we are applying the waste initiatives. Here is the key points about this project. So we can say the analysis reveals that all 4 initiatives contribute to emissions reduction and operation efficiency. Construction waste and MSW deliver the best balance between cost and environmental benefits. Early investment yields stronger return and risks are mitigated through planning and governance. This chart shows projected CO2 reduction over time. A yellow line, it shows CO2 reduction without applying for initiatives, while the red one, it shows the CO2 emissions by applying the initiatives, and we can notice that easily how's the benefit and significant added value if we applying for initiatives. To conclude, these waste strategies are aligned with the vision of a 2030 and net zero 2050 for KSA. Tools like net present value and MAC offer a clear guidance for investment. The success of these initiatives lies on the structured plan and private sector engagement and timely execution. Thank you.
Hello everyone, thank you for joining me. I'm Mohammad Hadi and I'll be presenting this assessment of sustainability initiatives and my focus would be on mobility. So firstly, let's go through the executive summary of my assessment. So this report consolidates the major risk associated with implementing the mobility initiative across the Kingdom of Saudi Arabia. So as our objective is to assess the risk management framework of the proposed sustainability mobility initiative, and we will be using risk register, risk matrix, and capex and opex. So the initiatives which we are going to assess are EV charging, walkable city, micromobility, and public transport. Let's move on to our introduction. So why are mobility initiatives important? So firstly, it aligns with Vision 2030. So Kingdom of Saudi Arabia has a Vision 2030 which calls for diversifying the economy, even enhancing quality of life and reducing dependence on oil, and mobility initiatives are a cornerstone to modern infrastructure to promote sustainable cities, even improve public health. Then we have environment sustainability, in which mobility initiatives such as EV, micromobility, and walkable public transport, they will all reduce greenhouse gas emission and air pollution and even fossil fuel consumption. Then the traffic congestion and urban efficiency. So there are major cities like Riyadh and Jeddah which face growing congestion due to urban sprawl and car dependency. So the public transport and walkable infrastructure would really help to ease the congestion. And then there's public health and livability, where active mobility options would improve population health and encourage social cohesion, such as like uh, encouraging walking and cycling. As we can see, these all has benefits. So, firstly, our carbon emissions are going to be reduced, and there's going to be job creation, and in the transport services, even clean tech and maintenance. And then there we are also trying to boost non-oil GDP through transport, tourism, logistics, and innovation sector. Then it will also improve the public health, as I said before, via walking. It will encourage walking and cycling. So moving on to my risk analysis, I'll be discussing two components in this part. It will be risk register and risk metrics. Quickly, so this here is the risk register for all my four initiatives. The risk IDs, you can see the risk with R represents the EV charging, risk with W represents the walkable city, M represents micromobility, and P represents public transport. So here I have a risk IDs, risk descriptions, and then likelihood and impact, and then their mitigation strategies. Then I have post mitigation strategies, and then we can also see the initial and post mitigation risk score and also differentiate in that. So this is my risk matrix. We can see that the red colored number 6 is basically the critical risks, the high risks, number 13 and 8, the yellow colored numbers are medium risks, and green colored number 10 is low risk, so which has very less impact and which is not important to be treated. The red risks are critical to be mitigated, and uh, they should be treated very timingly. Moving on to the next part, let's discuss the cost analysis of mobility initiatives. So this right here is capital expenditure for EV charging. So the top right graph shows us the baseline assumptions that we are going to install a 10,000 chargers, and which would be 70% would be level 2 charger and 30% would be fast charger in 40 major cities plus intercity corridors over the period of 5 to 7 years. And on the left, the graph shows us each component of the capex per station. So, and then we have nationwide capex estimate, which shows us that the total will cost us around, if it's uh, cost us around 1.05 billion to 1 point estimated 1.05 to 1.55 billion Saudi Riyal. So on the bottom right, I have put a three-phase plan for 7 years, which also shows us we shows us the unit we have to purchase per year uh, according to the phases, and then it also shows us the lowest total capex and the highest total capex, which is 1.045 million billion to the highest is 1.5 billion. So this is OPEX for EV charging. So the top left graph shows us the categories and on which we are going to decide the cost. And then the chart parallel to it, the table parallel to it basically shows us the total cost. So as I said before, you're going to use 70% of level 2, which is 7,000 level 2 charges and 3,000 DC charges. And we have annual OPEX cost range, and then we can calculate the total annual OPEX range, which is from approximately 145 million to 204 million Saudi Riyal. I've also put in the three-phase plan to complement the capex, and this also shows us that in phase one, our cost is going to be, if it's lower, it's going to be around uh, 65 million, and highest is going to be around 93 million, and the total lowest cost which we are going to face is 352 0.5 million to 495 million. So this right here is capital expenditure for walkable city. So first we can see that there are key walkable components, each listed differently, and then we can see the capex summary table. So this is basically for 500 kilometers. I've assumed that I'm making a walkable network across KSA. across KSA for 500 kilometers. So this cost is for that, and we have a low estimate and a high estimate. So the total capex cost for making a walkable city in Saudi Arabia of 500 kilometers is varies from 1.53 billion Saudi riyal to 3.48 billion Saudi riyal. So here is the OPEX for walkable city, and we can see each component separately with cost Saudi Real per kilometer per year, and also total for 500 kilometers. The details for each component is also given, like what type of maintenance, for example, inside when pavement where there can be cleaning, patching, or even leveling. So the annual OPEX summary for 500 kilometers, the lowest estimate is 71.5 million real, and the highest is 113.5 million real. So this right here shows that we are going to the OPEX for different cities like Riyadh, Jeddah, and Dammam. So we need to make 200 kilometers of walkable track in Riyadh. What is it going to cost, the OPEX? And it even shows the each cost of different components and the low and high cost. So we can take a look and plan accordingly. So this is capex for micromobility. As we can see in the breakdown of components, we are purchasing like 30,000 units of e-scooters and 20,000 units of bike, which is a fleet of 50,000 vehicles. And we can see each component separately with its units and total cost. So the total cost for capex would be, if we have a minimum estimate, it would cost around 418 million Saudi riyals, and the higher estimate would say 633 million Saudi riyals. So this is operational expenditure for micromobility, where we have different categories and cost per unit and fleets per unit and total annual cost, which will be around the lower estimate is 112.5 million real and higher estimate is 174.5 million real. Also, I have given note in the component table to understand the category. So, for example, this vehicle maintenance. So we have like parts, labor, software updates. Same goes for battery charging. We have electricity, labor, logistics. I've also given a city plan where we have like 10 cities. So I've included like big three cities, Riyadh, Jeddah, and Dammam, and allotted vehicles to it, also the stations. And then we can differentiate in the total OPEX cost for low and high. So this is capex for public transport. So we are going to target 10 major cities with 6,000 buses and 40 to 50 major depots with ticketing, GPS, and fleet management. So then there's breakdown where there's each component and per unit cost and the total units and the total cost. So the total capex cost is going to range around uh, capex cost for public transport is going to range around 11.7 billion Saudi Riyal to 16.95 billion Saudi Riyal. So lastly, this is OPEX for public transport. So we have different components like driver salaries, fuel, energy, maintenance, depot, and breakdown individually. And the total annual OPEX cost would range around 125 billion to 1.7 billion Saudi Riyal. And then I also have a city plan where in Riyadh, suppose you're gonna purchase 2,000, deploy 2,000 buses with 15 depots, and they're gonna be 1,500 stops. So the total cost would be around 3.3 billion Saudi Riyal, and the higher cost would be 4.8 billion Saudi Riyal. Also, we can see this annual OPEX cost for which is for both ranges low and high. Thank you. Moving on to my next part, findings. So first, this diagram shows box plot of initial versus post mitigation risk scores. So we can see the left box for the initial risk score, median lies around 20, the interquartile range is wide, and the middle of 50% of scores span roughly from 15 to 25, showing high variability. And then you see the second box, which is post mitigation score. We can see the median is around 10, which is a significant reduction. Even the IQR, which is interquartile range, is narrower and showing reduced variability and tighter risk control. This bar chart represents average risk score by category. The yellow chart shows, so there are three basically categories: financial, operational, and strategic. And the yellow chart shows the initial score, and the orange represents the post mitigation score. So we can see there's a significant decline in risk score after the mitigation in every category. So this bar chart represents total cost which is required to mitigate the risk according to their categories. So we see that operational risk requires the most cost to be mitigated. As we can see, it's more than 1,000 millions of the reals, and then strategic is the lowest around, which requires around 300 million reals, and financial requires around 650 million reals. So we'll be discussing key observations. So firstly, operational risks were the most frequent ones, which also required robust projects and traffic management strategies. And then there were three risks R3, W2, and M2, which remained even high after mitigation. And further, we will be discussing how to mitigate this risk and cost required to mitigate these risks. Now I will be discussing the MAC model. This right here is the marginal abatement cost curve. It is a tool to evaluate and compare cost effectiveness of emission reduction options, also quantify the carbon dioxide abatement potential for each initiative. It also helps prioritize investments and policy actions. The x-axis shows us the different mobility initiatives. The y-axis shows us the annual CO2 reduction in kilotons, and the label on each bar shows us the cost per ton of CO2 reduced. So firstly, I'm going to interpret EV charging. So you can see the cost per ton is 2 point almost 3 Saudi Riyal per ton, and then the annual CO2 reduction is 1800. So we can say it is cost effective and also has a high impact. And then there's micromobility, which has cost of 3.23, almost 3, with a 650 annual CO2 reduction, kilotons reduction. It also it's low cost, but is has a very moderate impact. Then we have walkable city, which is also around 4 Saudi Riyal per ton, the cost, and then the annual CO2 reduction is around 900. We can say it is medium on cost, also healthy, and has very livable benefits, and it is also good for the future of the society. And the last is public transport, which has a cost of around 5 Saudi Riyal per tons, uh, and then it has annual CO2 reduction of around 2400. So we can note that it has the highest impact, and it is also complemented by the highest cost. So these are the strategic recommendations out of my MAG model. So firstly, in short term, from 2025 to 2028, we can ramp up the EV charging infrastructure across cities and highways and promote micromobility zones near metro stations, university and offices. And then in the medium term, we can redesign cities for walkability. Begin with pilot areas such as Riyadh, Jeddah, Dammam. Also, Makkah Medina is a very good option and a very big tourist spot. So that can also be converted into a walkable city. And also we can start public transport extensions, especially bus lanes and park and ride systems. All and the lastly, in long term, we can integrate all systems into a multimodal smart mobility network, ensuring sustainability of public transport through subsidized apps, and service reliabilities. So moving on to my final part, let's talk about potential risk for mobility initiatives. Let's talk about my first initiative, EV charging. So, basically for risk R3, which was a critical one. So, as EV adoption increases, the demand for electricity will surge, especially during peak hours. If the grid is not prepared, this could lead to blackouts, voltage drops, or inefficient power distributions. So, in order to mitigate it, we had to collaborate with utilities for capacity planning and infrastructure upgrades. So, in order to do that, we could deploy smart charging solutions that manage charging off-peak hours and balance loads. Also invest in grid monitoring storage solutions, for example, backup batteries or even demand response system. So as you can see, this in order to mitigate this uh, risk, estimate of 3.0 million Saudi Riyal is predicted, which includes grid impact, smart charging software, limited infrastructure reinforcements, and partner development with utility companies. So for the second risk, as we know that the EV charging networks become digitally connected, they become target of cyber threat attacks and disrupt services, steal user data, or compromise national energy infrastructure. So this was also a 25 rating risk. In order to implement it, we had to use end-to-end encryptions, regular security audits, firewall, and intrusion detection system. So for mitigation, 2.4 million Saudi Riyal was expected, which included security audits, hardware and software security tools, cyber security training for operators, and monitoring and response infrastructure. So this right here is Walkable City, my second initiative, and it had only one critical risk. So as we all know that in Saudi Arabia, there's extreme heat, like often 45 degrees Celsius, and intense sun exposure with occasional sandstorms, which can make outdoor walking very uncomfortable or even unsafe for extended periods. So this undermines public use of pedestrian infrastructure, reducing the return on investment and defeating the purpose of sustainable urban mobility. So in order to mitigate that, we have different components like shaded infrastructure, heat reflective pavements, misting and cooling elements, urban lighting, and climate designs. I've also the cost range is also per kilometer, and the total cost is for 500 kilometers. So in order to mitigate this risk, we the in expected cost is around 425 million to 1.095 billion Saudi riyals. So this cost ensures the walkability is viable year round, even during peak summer months, and it is critical to be adopted in KSA. So moving on to my third initiative, micromobility, it also had one critical risk. So in fast-growing Saudi cities like Riyadh and Jeddah, urban streets are dominated by high-speed vehicle traffic. Include introducing micromobilities like e-scooters or e-bike would without protected infrastructure could lead to accident risk, public fear, and low adoption, even liability issue for operators and opposite from road users and regulators. So in order to mitigate it, we could build protective lanes, establish clear road signage, and enforce tech. Also, we could use public safety campaigns and training. Also, we could use policy framework and traffic law integration. So I've also put costs for each initiative per kilometer and the total cost, which is around 1,000 kilometers in micromobility lanes, and it is also rolled out in 10 major cities. So moving on to my last initiative, which is public transport. So this had two critical risks. So firstly, talking about P1, which was low public usage due to culture preference for private vehicles. So we know that Saudi has a long-standing car-oriented culture, which is enabled by low fuel cost and road-dominant urban designs. Also, there's a social preference for driving. So without strong incentive or public appeal, public transport would remain underutilized despite infrastructural investments. So in order to mitigate these, I have given different mitigation components. So you can run national awareness campaigns, then launch mobile apps and real-time info systems. Also use TOD policy and pilot sites in 5 cities. So TOD is transit-oriented development. And then we could use service level agreements and bus optimization. And also the costs associated is written there. And then for the second risk, P3, which is high capital and operational costs with slow return on investment. So we know that there's large upfront investments in fleet and infrastructure, and operations may not yield quick returns. So public transport in early phases may run a deficit. Without proper planning, this might become fiscally unsustainable. So in order to mitigate, we have PPP and legal framework development. For example, like diversified funding from government, sovereign fund, World Bank, and then we have a long-term sustainability buffer for the first 5 years. Then we have commercial space integration at 100 terminals. So we can use phase scaling. We could start with high density corridors and then we could expand them later. And then there's advertising and branding setup, and also the cost associated is written with it. So lastly, for recommendations, firstly, you could prioritize mitigation for high impact and high likelihood risk, like risk ID R3 and P3. Then you could expedite regulatory reforms and planning approval for public transport and micromobility. Also secure long-term funding mechanism, especially for heavy capital items like public transit and charging infrastructures. Then you could use public awareness and incentive programs to drive model shift away from private vehicle dependency. And then lastly, you can monitor and update mitigation strategies regularly with performance data and community feedback.